Hey everyone, and welcome back to DevOps Corner. You've probably been told that Kubernetes' best practice is one container per pod. It's like rule number one. But here's the thing. The massive, real-world systems you use every day, think Netflix, think Google, they are built unintentionally breaking that rule. Every single day.
So that raises a pretty big question, right? If the single container model is supposed to be the gold standard, why are the most advanced engineering teams on the planet building their entire infrastructure around pods with 2, 3, or even more containers? The answer isn't that the best practice is wrong. It's just incomplete. It's the hello world of Kubernetes. It's what you do before you run into the kind of messy, real-world problems that don't have a clean textbook answer, the kind of problems that actually define production engineering.
All right, so before we completely tear this rule apart, let's give it some credit. There's a really good reason this became the standard in the first place, and you absolutely need to understand why before we go any further.
And this is why it usually works so well. I mean, you can think of it as the microservices manifesto, just applied to your infrastructure. Each pod becomes this perfect isolated little box. Your web server scales, your database scales, all completely independently. If one API service pod dies, it doesn't take anything else down with it. It's clean, it's simple, and honestly, for like 80% of your services, it's exactly what you want.
But we don't get paid to solve that easy 80%, do we? We get paid to solve the messy, complicated 20%. The part where that clean, theoretical world of best practices just shatters against the hard reality of a production system. This is where the one container rule breaks down.
I really want you to picture this scene, because I guarantee someone watching has lived through this exact nightmare. You've got this critical, ancient legacy app. It's running in a container, it's doing its job, but it's just spewing logs to a local file. Then the mandate comes down from management. All logs must go to our central logging system. And then, here comes the knockout punch. You are absolutely, under no circumstances, allowed to touch the source code. So, what do? In a one-container world, you are completely trapped. You can't just apt-get install a logging agent into the container, right? That just pollutes your image and creates this weird two-headed monster. And you can't change the app to log to standard out. The standard pattern gives you absolutely no way out. It is a dead end.
And this exact frustrating problem is why the sidecar pattern even exists. It wasn't dreamed up in some academic lab. It was hacked together late one night by an engineer who is completely and totally stuck. It is the ultimate answer to the question, how do I bolt new functionality onto an application that I cannot change?
So what is it, really? Well, a sidecar is just another container that lives inside the exact same pod as your main application. You know, like a motorcycle sidecar. It's attached, it goes on the same journey, but it has its own distinct purpose. It's there to provide these supporting services, handling all those cross-cutting concerns that your main application really shouldn't have to think about.
And this is the technical magic that makes it all possible. A pod is so much more than just a box for a container. It's a shared execution boundary. Think about what that actually means for a second. Shared network. Your app and the sidecar can talk to each other on localhost. We're talking memory speed communication, no network hops, zero latency. Shared storage. One container can write a file to a volume and the other can read it instantly. And a shared lifecycle. They are born together and they die together. This isn't just a convenient grouping, it's a fundamental unit of colocation.
Okay, so now that we get the how, let's really dig into the what, because this simple idea is the foundation for some of the most powerful and complex systems running in the cloud today. This is not just some neat trick for old apps. This is the engine behind entire platforms.
Let's go right back to our legacy app nightmare. With this sidecar pattern, the solution becomes, well, almost elegant. We run our main app in one container. And right next to it, in the same pod, we deploy a tiny little logging agent like Fluent as a sidecar.
And here's how it works. In our pod spec, we define a simple shared empty-dir volume. Our legacy app container mounts that volume at var/log and just does its thing, writing its log file, completely oblivious to the outside world. Then the FluentD sidecar mounts that exact same folder and just tails the file. It sees new lines, grabs them, and ships them off to our central system. The main application has zero clue this is even happening. We've surgically added functionality without touching the patient. Problem solved? Okay, so that's a simple but really powerful use case. But now let's look at where this pattern leads when you take it to its absolute extreme, the service mesh. If you've ever used Istio or Linkerd, you have been living in a world built on sidecars, even if you didn't realize it. Now I really want you to focus on this, because this is a key insight. A service mesh, when you strip away all the marketing, is nothing more than a highly sophisticated, automated system for injecting a sidecar proxy next to every single application you run. That's it. This sidecar, which is usually an Envoy proxy, gets automatically injected and configured to intercept every single packet of network traffic going in or out of your application container. And just like that, without you writing a single line of application code, your entire system gets automatic mutual TLS encryption, rich observability metrics, distributed tracing, and advanced traffic control like circuit breaking. It's a whole platform of features just gifted to your applications, all thanks to this one pattern. By the way, if this is changing how you think about Kubernetes architecture, do me a favor and hit that like and subscribe button. Our next deep dive is going to be on exactly how service meshes use this trick to manage traffic at massive scale. You don't want to miss it. So at this point, sidecars sound like pure magic, right? They solve impossible problems, they unlock these incredible features. But here's the catch. They are not free. This is the part of the story that's often left out of the tutorials. This power comes with a steep price, and this is where a lot of teams get burned.
First, the most obvious cost, resources. Every single sidecar you add is another process consuming CPU and memory. Yeah, a little Fluentd agent might be tiny, but an Envoy proxy for a service mesh? Not so much. Now multiply that overhead by the 500 pods in your cluster. You are now paying a constant cluster-wide sidecar tax that can easily add 20 to 30% to your cloud bill and can cripple the number of workloads you can pack onto your nodes.
And now for the one that bites everyone. Seriously, this is where most engineers get it completely wrong: pod startup order. Inside a pod, there is absolutely no guaranteed start order for your containers. So imagine your app boots up in, say, half a second and immediately tries to connect to the database. But its network traffic has to go through the service mesh sidecar. What if that sidecar takes 3 seconds to initialize? Well, your app's connection fails. It panics and crashes. Kubernetes restarts it, it comes up fast again, the sidecar is still not ready, and it crashes again. Welcome to crash loop back-off hell. You will spend hours debugging this, thinking your app is broken, when the real problem is a race condition happening inside your own pod.
And finally, there's the long-term operational pain. Look, debugging a single container is pretty straightforward. Debugging 2 containers that share a lifecycle in a network is exponentially harder. When something goes wrong, whose logs do you check first? How do you correlate a timestamp from the app with one from the sidecar? And what happens when your sidecar proxy suddenly eats all the CPU, starving your main application? You've just created a noisy neighbor problem inside your pod. You've traded application simplicity for a massive dose of operational complexity.
So, given all these costs, the most important skill here is knowing when to use this powerful tool and when to leave it in the toolbox. This is the difference between blindly following a pattern and making a deliberate, thoughtful engineering decision.
Let's start with a really common mistake. If your goal is to grab logs from every application on a given node, using a sidecar is a massive anti-pattern. You'll end up running 50 identical copies of your logging agent on one machine, all fighting for resources. The right tool for this job is a daemon set. It runs exactly one copy of your agent per node. That one agent can then collect logs from every other container on that machine. It's purpose-built for node-level tasks, and it is infinitely more efficient. And the next question you have to ask is, do I really need to be this close? The whole point of a sidecar is that zero-latency localhost communication and shared file system access. If your helper function can handle a tiny 2-millisecond network round trip, it probably doesn't need to be a sidecar. It can just be its own microservice. Building a single, scalable authentication service is almost always a better idea than injecting an auth sidecar into every single pod. Don't pay that resource tax if you don't absolutely need to live in the same house.
And that brings us to the one question you have to ask every single time you think about using this pattern. Does the benefit of decoupling this one specific concern justify the massive increase in operational complexity and resource cost that comes with it? For our legacy app, the answer was a clear yes. For a service mesh providing platform-wide MTLS, it's almost certainly a yes. But for that custom caching layer you were thinking about building, maybe not. The one container, one pod rule isn't wrong. It's just the default. Knowing when, why, and how to consciously break that rule and being able to justify the cost, that's what separates a junior engineer from a true system architect. If this deep dive into engineering trade-offs was useful, make sure to hit subscribe because we're going even deeper next time into the world of Kubernetes networking and how all these services actually talk to each other. See you then.